Hi, okay, we're going to go over the review sheet. So the first 5 questions are optimization. So with optimization, you got to get an equation in one variable, take the derivative, set it equal to 0, check if it's a maximum using the second derivative, and then fill in your answers. So our first problem, we've got a barn, right? And then against the barn, we have fencing on 3 sides. So we don't need fencing there, but we need fencing on these other 3 sides. So it says let the length be the side that's parallel to the barn. So this is the length, and the other dimension would be the width. Now, you're trying to find the dimensions of the field with the maximum area. So your primary equation is going to be the area of this plot. So area, we know, equals length times width. We have to get that in one variable. Well, they told us that the total amount of fencing equals 200 feet. That gives us a secondary equation to work with. So that tells us that W plus L plus W, or 2W plus L, must equal 200 feet. So L equals 200 minus 2W. So you use the secondary equation, like for parts, you're using it to solve for one of the unknowns. So you're going to take what we got for L in this one, and it doesn't matter which one you solve for, I solve for L, and you're going to substitute it into your primary equation. So 200 minus 2W times W. So now I know my area is equal to 200W minus 2W squared. Now W is the length or the width of the fence. So I just want to make sure at the end that I don't get a number that's negative. So I want to make sure W is greater than 0 and less than, it would have to be 100 because you have 2 of the W's. You only have 200 feet. So make sure, you know, at the end our answer is somewhere between 0 and 100. But once you get your equation in terms of one variable, you just get the derivative, 200 minus 4W, set it equal to 0. So if I add 4W to both sides, I have 200 minus, oh, I meant to say equals, positive 4W, and divide. And so we get W equals 50. Now we want to make sure that that's going to give us a maximum area, not a min. So what we do to check is we get the second derivative, which would just be negative 4. So even if I plug the 50 into the second derivative, it's still always negative 4, right? Let me just write that down a little better. All right, so the second derivative equals negative 4. So the second derivative at when W is 50 is negative, okay? And if it's negative, that means the graph's concave down, all right? So it's a maximum area. So that's the one, we do want that area, that to be our value for W. So we know the width is 50. To get the length, go back to that secondary equation, go back here, all right, and plug in the 50 that you got for W to figure out that the length is going to be 100, because 200 minus 2 times 50 is 100. So the optimal width we found was 50. We went back to the secondary equation, plugged in at 50, and found that the length was 100. And so the optimal area is our length times width, so that's 5,000. And this was, I think, square feet. This would be, you don't have to write units for these, so I don't care. I'll write them just to be right. Okay? Now for the next one, you can always pause. I got to erase this. Yep. For the next one, we have a rectangular page that's to contain 24 inches of print. The margins at the top and bottom are 1.5 inches, and the margins on left and right are 1 inch. What should be the dimensions of the page so that the least amount of paper is used? So they want the overall dimensions to minimize the area of the paper. Now, the area of the whole paper would be whatever this is, I'll call that the length, times whatever this is, I'll call that the width. Right? But what we don't know, even though we know the margins, we don't know what this length is here. So I'm just going to call that y. And we also don't know what this length is here. So I'm going to call that x. But the entire length of the page would be 1.5, right? This is 1.5 plus y plus another 1.5. So the length of the page, the way I've labeled it, is y plus 3, because y plus 1.5 plus 1.5 is y plus 3. The width of the page will be, you've got the 1-inch margin on the left and the 1-inch margin on the right. So altogether, it'd be x plus 1 or x plus 2. Okay, so I've got an equation, but again, it's got to be in one variable. So I need another equation. They had to have given me some other number, or some other information, so I could write another equation. And that is that the area with the printing, that's what's inside here, is 24 square inches. So that means that x times y, the area of the printed material, must equal 24. So this is what you're going to use to solve for either x or y. Doesn't matter. I'll solve for y. So if I divide each side by x, I see that y equals 24 over x. So I plug that in for y. And I now have an equation for the area in terms of one variable. So now, after we multiply it out, we'll take the derivative and set it equal to 0. Okay, so when you multiply it out, I don't know, you kids use the box method. I just double distribute. So 24 over x times x is just 24. 24 over x times 2 is 48 over x. 3 times x is 3x. Plus 3 times 2 is plus 6. So the area that I have is 20. Oh, I can combine the 24 and the 6. Let's just make that 30. So it's 30 plus 48 over x. I'm just going to write that as 48x to the negative 1. That way I don't have to use the quotient rule to get the derivative. And then plus 3x. Okay. So now let's get the derivative and set it equal to 0. So the derivative equals negative 48x to the negative 2 plus 3. Once you get the, one thing I didn't say here, as far as what x can be, all we really know is that it's got to be positive. So hopefully we'll come back with a positive number. So, okay, we set our derivative equal to 0. So when we set the negative 48 over x squared, right, that's plus 3 equal to 0, we can solve this by adding 48 over x squared to both sides. So I have 3 equals 48 over x squared. You can then cross multiply, right? So we have 3x squared equals 48. So x does have to be positive, right? It's like the width of the printed material. So it's going to have to be 4. If x squared is 16, x would be 4. Now, just to make sure this is giving us a minimum total area and not a max, let's just get the second derivative. So the second derivative would be, and I'm looking over here at the first, would be 96x to the negative 3, or 96 over x cubed. If I take that answer that I got, that made my first derivative 0, 4, and I plug that into the second derivative, 96 over 4 cubed, we don't care what it is. What we care is that it's positive. And if the second derivative is positive, the area function is concave up there, right? So you have a min. So it's what we wanted, minimum area, when we let x equals 4. All right. Now, to get the y value, we can go back to that secondary equation. Remember that secondary equation? We had y equals 24 over x. So if we put the value for x we found in, we get 6. So we know now that in order to make the area of the whole paper a minimum, we need to make x4 and y6. But now we got to be careful here because
Mr. Sullivan, please contact the main office.
We were asked to find the width and the length of the whole paper. So remember the length was y plus 3. We figured out y was 6. So the length is 6 plus 3, which is 9. I guess this is in inches. Doesn't matter. The width of the paper, right, we said was x plus 2. We figured out x is 4. And if you take 4 and add 2 to it, you get 6. So this would be the width and the length of the entire poster, including the printed material and the margins. Okay. Sorry about how this is kind of too small. So I got to keep erasing. All right. Okay. In our next problem, we've got, let me just erase this. Okay, the next problem, we have find the largest area of the rectangle that can be inscribed or can be drawn with one side along the x-axis and its upper two vertices on the graph y equals 9 minus x squared. So we don't know, the whole key to this is finding out what the coordinates of this point are going to be that are going to make that area as large as possible. Well, so we're trying to maximize area. So once again, we need an area. We need a formula for the area of this rectangle. Now I know area is length times width, right? Let's say that we make this the width. And you don't have to have this step length times width there. I just want you to see where I'm going to get everything from. So let's say I'm calling this the width, and I'm calling this dimension the length. The width, okay, this distance here is whatever the y coordinate is of that point. It's just what y is. So in for the width, I'm going to put y. Now for the length is the distance all the way across. The x coordinate only gets me the distance from the y-axis. If I want to get the whole length, I got to double that. So the length of a rectangle would be 2x. So now I've got my formula for the area of this rectangle with this labeling is 2x times y. It's in two variables. So once again, we need another equation to use to substitute into this one. And it's right here. For any point on this parabola, y equals 9 minus x squared. So we substitute that in. We multiply it out. The x coordinate of this point, once you get an equation in one variable, it's always nice to take a look and say, well, what kind of numbers could I get for this? Well, x is the x coordinate of a point in the first quadrant. So you know for sure that x is going to be greater than 0. Right? But it would have to be, even if it went all the way down here, this crosses here at 3, it's got to be less than 3, right? Or you're not going to be up above the x-axis. All right, so we need to get an answer that's between 0 and 3. Let's go get it. We get the derivative. Once we get the derivative, we're going to set it equal to 0. I'll add a 6x squared to both sides. I could have factored also. Divide by 6. So I have x squared equals 3. Now x has to be positive. See, that's why it helps to look to see the interval that makes sense. So x is going to be equal to the positive square root of 3. Usually we take plus or minus the positive square root of 3. Okay, now we got to do a little safety check. We got to make sure that gives us a maximum area and not a minimum. So we're going to go back to where we had the first derivative, figure out what the second derivative is. The second derivative is negative 12x. If we plug the answer we got into the second derivative, so rad 3 in there, you see we're going to get a negative number. Negative 12 times rad 3 is negative. If the second derivative is negative, the function's concave down, that means we must have a maximum area if we let x equal rad 3. That's what we wanted, the maximum area. Okay, now let's go back and figure out the other unknown. Let's get the y. Remember y in that secondary equation was equal to 9 minus x squared. So if I go back to that and put in the x that I found, 9 minus 3 equals 6. So now I know the coordinates of that point that make that rectangle as large as possible. So what we just found is if x is rad 3 and y is 6, that rectangle will be as large as possible. Now they want us to actually find that area. Area, if you remember, was 2x times y. So we found, so our maximum area then, x we found was rad 3, excuse me.
Please contact the main office.
2 rad 3, right, 2x, and y we got was 6. So we get 12 rad 3. So that would be the optimal area, the greatest area that of a rectangle that can be placed under there. That'd be square units, but they didn't give us units. All right, hope you like this. Okay, 4 is the classic box problem. You're starting with a piece of sheet metal this time, and its measurements are 5 by 10 feet. Right? Yes, you're cutting out squares. Now you don't know what the sides of the squares are, so that's why any unknown length, and with these problems, you give it a variable, x. So you cut out 4 equal squares, and you fold the sides up, and that creates a box. So any of these squares here are thrown away, and you fold up the sides. Now, we're trying to find the maximum volume of this rectangular solid. So we need to write volume, a formula for volume, because that's what we're trying to optimize. So length times width times height. Right? Now let's say I call this dimension the length. That would equal the whole thing, which was 10, minus 2x, because you cut an x out of each side. So for the length, oops, sorry about the changing colors. So the length would be 10 minus 2x. Right? The width, if I call this the width, would be the whole side, which was 5, again minus 2x. And the height, when you fold up the side, when you fold these sides up, would be x. All right, so the height is just going to be x. Now, what's kind of nice about this problem is it's already in one variable. All you got to do is get the derivative, set it equal to 0. Bam. The only thing is we've got to multiply it out first. So if you multiply this out, okay, you could distribute or use whatever box method for the first 2 factors and then distribute in the x. All right. Just going to get my work. Okay, so 5 times 7, so we have 50 minus 20x minus 10x plus 4x squared, right? And we still have to multiply by the x. So if I combine the negative 20x and the minus 10x, that's minus 30x, and I distribute the x, I get the volume is equal to 4x cubed minus 30x squared plus 50x. Beautiful. Now and as far as what can x be, what kind of numbers make sense in this problem? X, the length of the side of the square, would have to again be positive, but less than half the side of half the length of the shorter side. So it's going to have to be less than 2.5. You can't cut anything else. You can't cut anything greater than that. All right, you don't have enough. So we get the derivative, 12x squared minus 60x plus 50. And we set it equal to 0. And I'm sorry, this one doesn't factor. So to solve 12x squared minus 60x plus 50 equal to 0, you have to use the quadratic formula. Now, you could divide both sides by 2 to make the numbers a little bit more manageable. you can divide both sides of an equation by 2, right? The sides are still equal. So you'd have 6x squared minus 30x plus 25 equals 0. But that's it. Now, we can't factor, so we're going to use quadratic formula. X equals negative b is 30 plus or minus the square root. B squared, negative 30 squared is 900 minus 4 times 6, so minus 24 times c is 25, because it's minus 4ac, all over 2a. 2 times 6 is 12. So if you 24 times 25, I believe that's going to be 600. So 900 minus 600 is 300. So we have x equals 30 plus or minus the square root of 300 over 12. Now, I'm not even going to bother breaking down the radical, okay? We're just going to write down what the two answers are, because we can use our calculator with this. So one of the answers, when you use this with the minus, you're going to get 1.057. The other answer, if you use the plus, you get x equals 3.943. So this could cause a problem, but if you remember that x, the side of the square, had to be between 0 and 2.5, then you would know, oh, I have to reject that. That's not even possible, right? So now we think this is the answer. Just to make sure, we'll get the second derivative. So let me go back to where I had the first derivative. So the second derivative is equal to 24x minus 60. And if I were to plug in that 1.057 into it, it's going to be negative, which means my volume function has a max there. So I have a maximum volume. Now let's go and answer the question. So we know what side squares to cut. So the side of the square we found out was 1.057 feet. The maximum volume you can get by just looking at your equation for the volume after you cleaned it up. You can just plug in here, or you can figure out the other dimensions too. Any of these you can use, okay? Plug in the x you got, and if you do that, I believe you have 24.056 cubic feet. Okay. So that, oh, we still have to do 5. We have one more optimization problem. I know these take a little while. Oh, but they're so fun. Okay, one more optimization problem. Okay, we've been asked to design a 30 cubic inch can, so that's got to be what it holds. All right. Now, right circular cylinder. Well, we're given the volume and we're given the area. So actually, add a surface area form. I don't even need to use up my space. Okay, but what we're trying to do is minimize the amount of material used. So what we're trying to minimize is the surface area. So this is our primary equation. This is what we're trying to minimize. So that's what I start with. Right? But that's the one you got to get in one variable. Right? So to get rid of one of the variables, you have to look, how can I write another equation? Look for the number. If they give you a number, usually that's the clue. So that's the volume. So that must mean that 30 equals pi r squared h. Right? So this is what we're going to use to solve for one of the unknowns. I'm going to solve for h. It's easier. So we can divide each side by pi r squared. So now we know that h is equal to 30 over pi r squared. So I put that into the h here. Pi r squared plus 2 pi r times 30 over pi r squared. Now, before I take the derivative and set it equal to 0, let's simplify this. The pi's cancel. One of the r's cancels. So the second term, 2 pi r squared, is just going to be 60 over r. So I'm going to write that as 60 times r to the negative 1. Makes it easier to take the derivative. Now, the variable here, r, all we really know is it's got to be positive. So let's make sure we come back with a positive number. Let's get the derivative. Oops, so the derivative would be 4 pi r minus 60 r to the negative 2. See, it's nice that I rewrote it as 60 r to the negative 1. If I left it as 60 over r, I'd use the quotient rule, and I'd get myself all confused in the minutia. Don't want to do that. Okay, so we got the derivative. Now we got to set it equal to 0. Well, if I have to solve something equal to 0, I'm not going to write it with negative exponents. I'm going to rewrite it without them. So we set the derivative equal to 0. Add the negative term to both sides. So we have 4 pi r. We're adding 60 over r squared to both sides. So it would be positive 60 over r squared. We can then cross multiply. So we have 4 pi r cubed, right, equals 60. We can divide each side. You know what? I'm going to divide each side by, well, I'll do by the 4 pi right away. Okay, so that'll be gone. Now, I have 60 over 4 pi. Well, 4 goes into 4 once. It goes into 60 15. So that gives me that r cubed equals 15 over pi. So then r would be the cube root of 15 over pi. Okay, so now we just want to make sure. And that, by the way, if you went to your calculator, that comes out roughly to be about 1.684. All right, but let's make sure that that gives us a minimum area, not a max. So go back to where you had your first derivative and get the second derivative. So that would be 4 pi plus 120 r to the negative 3. So it's 4 pi plus 120 over r cubed. If I took that number that I got, that was the cube root of 15 over pi, it's positive, that's all I care about, and I plugged it into the second derivative, both terms are positive, so that's definitely positive, which means my surface area function's concave up there, so I do have a minimum surface area when I let r equal the cube root of 15 over pi. All right, so we got our answer. Now we just got to fill in any blanks over here. So you could write the cube root of 15 over pi. Remember, to get the other variable, if you have one, go back to that secondary equation. I have it over here. So to get what h is, plug in the variable you found in. So it'd be the cube root of 15 over pi squared, or just 15 over pi to the 2/3. Or you could write the cube root squared. All right, so you can either leave it like that. All right, so 30 over pi times 15 over pi to the 2/3. I know it's ugly, but who cares? Now, if you wanted to put that in your calculator to see what it is, 684, I believe that's about 3.368 inches. Okay, so that's the end of the optimization. They take a while, but if you see with every one of them, you just need that primary equation, whatever you're trying to optimize, but you got to get in one variable. So if it's not, you got to write another equation, use it to solve for one of the variables. Get your primary equation in one variable, then you just take the derivative, set it equal to 0, and make sure the value you get is the one you want. Okay, part 2, related rates. This is better. Okay, so the first problem involves the volume of a cube. Now, when you have a cube, all the sides are the same. I'll call them x. So the volume of a cube is x cubed. That's length times width times height, but they're all x, so it's x cubed. The surface area of a cube, the area of each surface is x squared, So you add up all 6 sides, you get 6x squared. Okay, so first thing we do, we got a diagram, we labeled it. The volume of a cube is increasing at the rate of 20 cubic centimeters per second. So dV, the change in volume, the change in time, dV dt, is positive because it's increasing 20 cubic centimeters per second. So they gave us dV dt. And they're asking us how fast in square centimeters per second is the surface area of the cube increasing. So they're asking us what is change in area over change in time, the rate at which, at the instant when each edge of the cube is 10 centimeters long, so when x equals 10. Okay. Well, the fact that they gave us the dV dt, I'm going to write the formula down for volume of a cube. The volume is x cubed. So that when I take the derivative of it, I'll have a dV dt. So you take the derivative of each side with respect to t now. Now we're doing this because things are changing. So 3x squared dx dt. Now, I know what to fill in for dV dt. That's 20. I know to fill in 10 for x. But what this is going to allow me to figure out is the rate at which x is changing, dx dt. So if I just divide each side by 300, I get dx dt, 20 over 300 would be 2 over 30, or 1/15. And that would be in centimeters per second. But the problem is that's not the one they wanted. I was able to get that one with the volume equation, but now we're going to go ahead and get what they asked for us. They asked us for dA dt. So we're going to write now the equation for the surface area of a cube, which is 6x squared. We'll take the derivative of each side of this. And now we can plug in the 10 for the x. Dx dt we figured out was 1 over 15. All right. So if we take 12 times 10 times 1/15, we get 8. And that would be in centimeters squared per second. So that's the one they wanted here. So this one was just a little tricky in the sense that, oh, you had to get dx dt first before you could get dA dt. Okay. So 7. A spherical balloon. Let's draw it up here. Is being inflated at the constant rate of 5 cubic inches per minute. So that's because of the units, I know that that's dV dt, because you measure in volume in cubic units. And because it's being inflated, the volume's increasing, so I make it positive 5 cubic inches per minute. Okay. When the radius of the balloon is 4 inches, so when r equals 4 inches, A, how fast is the radius of the balloon changing? So for A, they're asking us for dr dt. Okay. So they gave us dV dt, they want dr dt. I'm going to write the equation for the volume of a sphere. So the volume of a sphere is 4/3 pi r cubed. Take the derivative of each side with respect to t, and then we can plug and shove. So we're putting in 5 for dV dt. R we said was 4. And now we'll be able to solve for dr dt. This is an r here. Okay. So if you multiply 4 by 16, that's 64. This is 64 pi here. So if we divide each side by 64 pi, we can solve for dr dt, which is what we're looking for. And the units, because length is measured in inches here, would be inches per minute. So just squeeze that in here, inches per minute. So that would be the answer to part A. How fast is the radius changing? That's dRdt. Now we know what dRdt is, we can answer the second part. How fast is the surface area of the balloon changing? So let's write a formula for the surface area. The surface area of a sphere equals 4 pi r squared. When you take the derivative of both sides, you get dA dt is equal to 8 pi r dr/dt. So we know that after you take the derivative, that's when you plug in temporary values, right? Like when r is 4. You know, r wasn't 4 the whole time. That's why I had to wait. dr/dt we figured out was 64 pi. And when we clean all this up for dA dt, okay, we have 8 times 4 is 32. So, well, at least the pi's would cancel. You see that, right? 8 times 4 is 32. 32 goes into itself once, into 64 twice. So it looks like you're just left. Oh, wait a minute. Why did I? Ooh, the pi is supposed to cancel. I'm just making sure. Yeah. Okay, so the pi should cancel because on the key I think I have 5 pi over 2. It should just be 5/2 square inches per minute. Okay, so that's what we're looking for. That's part B. Pi r. Yeah, that should have canceled. Okay. Just change that. Okay, so that was our little sphere-related rates. Next problem, number 8. Give myself a little room here. Okay. Two cars are riding on two different roads that meet at a 90-degree angle. Car A is 3 miles south of the intersection, traveling north. All right, so here's the point of intersection. So car A is down here, all right, but it's traveling north. So well, let's just first label this. So here's car A, and then car B is 2 miles east of the intersection. So car B is over here. And let me see, car A is 3 miles south, traveling north, so it's traveling in that direction. Car B is 2 miles east, and it's traveling east, so it's traveling in that direction. Okay, it's traveling east. All right, I'm just putting this up here for you. We'll make this north, south, east, west. Okay. Now, you need to, these lengths are changing. Remember, anytime you're setting up your problem, if a length's changing, put a variable on it. So I'm going to call this length y and that length x. Okay? Now, I think I will fill in what they're asking us for. How fast is the distance between them changing? So that's changing also. So we got to give that another variable. I think I will call that z. Okay. Let's figure out what derivatives they gave us. So first of all, we have car A. It's south and it's traveling north. So that means that y is decreasing, right? So dy dt, the rate at which that length y is changing, is negative 40 miles per hour. Car B is 2 miles east of the intersection. Remember, we said that that distance here was x. And it's traveling east, so x is going to be increasing at a rate of 50 miles per hour. So dx dt equals positive 50 miles per hour. And they're asking us how fast is the distance between the two cars changing at the moment when A is 3 miles south. So when y is, we're looking for dz dt when said A is 3 miles south. So that means when y equals 3 and B is 2 miles east. So when and x equals 2. So So we have dy dt, dx dt, we're looking for dz dt. That was a lot of translating in this one. So we've got Pythagorean theorem links these together. There's our equation. Take the derivative of both sides with respect to t. Remember with Pythagorean theorem, because if you have an equation, you can divide each side of the equation by 2, so you can get rid of the 2's. Then we go to plug and chug. So they told us when x is 2, I put a 2 in here. They told us dx dt is 50, I put a 50 in here. They told us y is 3. Again, these are temporary values, because now y is not 3 all the time. That's why I had to wait till after I took the derivative to put in these numbers. And dy dt is negative 40. Now, they didn't tell us what z is, but you can always figure it out because it's still a right triangle. So when y is 3 and x is 2, we know that 3 squared plus 2 squared equals z squared. Ooh, my z's. So 9 plus 4, so 13 equals z squared, or z is the positive square root of 13. So sometimes for that third side of your right triangle, you got to use Pythagorean theorem when it comes to plugging and chugging. Square root of 13 dz dt. So now, if we add up, we have 100 minus 120, so that would be negative 20 equals rad 13 dz dt. Divide by the rad 13. Oops. We've got our dz dt, and that's going to be in miles per hour. So we could leave it like that, or if you want to approximate it, it's, so my answer for dz dt, let me just write this out. You can leave it exact as negative 20 over rad 13, okay, miles per hour, or which is approximately equal to negative 5.547 miles per hour. So if you use your calculator, just be accurate to 3 places after the decimal. Okay. Number 9. Oops. Okay. A right triangle, let's lift this up. A right triangle whose sides are changing has sides of 30 and 40 inches at a particular instant. Those are temporary values, so we don't use those. Let me just draw my right triangle. So these sides are changing. So right away I'm going to put variables on them. It says if the shorter of these two sides is increasing, now I'll just let the shorter side, I'll call that y. It doesn't matter what you call it. Let's make the longer. So if the shorter of these two sides is increasing at a rate of 3 inches per second, so if dy dt is equal to positive 3 inches per second, and the longer side, which I called x, is decreasing at 5 inches per second, so that means dx dt equals negative 5 inches per second. How fast is the area changing? So let's do part A first. So part A, we're asking for the rate at which the area is changing. Okay, we'll answer this one first. So if we want to get dA dt, we're going to need the area formula first. So area of a triangle equals 1/2 base times height. Now, I called my base x, and I called my height, oh, sorry, I called my height y. So we're going to take the, after you have your equation, you know, it's not like optimization where you got to get in terms of one variable. And you got the derivatives. If we take the derivative right now, we'll wind up with dA dt, dx dt, dy dt. We got 2 out of 3 of those, so we don't have to get this in terms of one variable. So we just go ahead, we take the derivative. You know, you can either keep the half out or you know, keep it as the first. I'll keep with the first this time. So let's say that that's my first when I use the product rule, and the y is my second, all right? It's a, you could just pull the half out and just do the product rule with x as the first and y as the second. I'll just do it this way. So we have first times derivative of the second with respect to t plus the second times the derivative of the first. So it's after you take the derivative, you can plug in those temporary values, all right? Because they asked us to find at the moment when the shorter side is 30. So we're trying to find the ADT when the shorter side is, so when y equals 30 and the longer side called x equals 40. All right, forgot to write that. So now we can plug in Chuck. We're looking for the ADT. So for x, we're going to put in the 40. For dy dt, we put in the 3. For y, we put in 30. And dx dt, we put in negative 5. So 1/2 of 40 is 20 times 3 is 60. 1/2 of 30 is 15 times negative 5 is negative 75. So we get, for dAdt, negative 15. And for the units of area, because length in this problem was measured in inches, it'd be square inches per second. All right, so all that is part A, because we were looking for the ADT. Now we're going to move on, and we're just going to do part B. We're looking for the rate at which the hypotenuse is changing. Well, that's changing, so I better put a variable on it so I would know what to call it. I'm going to call it Z again. Oh, you know what? Let's call it H, because my Z's aren't the best. I'm going to call it H. All right, that's changing, so I put a letter on it, whatever you want to call it. All right, I'm going to leave all my given stuff because that's still good for this. But now, instead of finding the ADT, we have to find, for part B, we have to find the HDT, right, when all this other stuff is true. So we need to have an equation that has H in it. So when I take the derivative, I'll have a dHdt. So good old Pythagorean theorem. When you have, you know, the sides of a right triangle, no angles involved, right? They're not asking for area. Pythagorean theorem ties them together. So you know x squared plus y squared equals h squared. Differentiate with respect to t, 2x dx dt plus 2y dy dt equals 2h dh dt. And again, with Pythagorean theorem, you can just divide out the 2's, divide both sides by 2, and now we just plug and chug. So we're looking for the HDT. We're plugging in for x 40. Dx dt gets a negative 5. For y, we get to plug in 30. dy dt is 3. Now, again, see, sometimes with Pythagorean theorem, oh, you know what the temporary value is for x and y, but you don't know what it would be for h at that moment. But you can figure it out, because when y is 30 and x is 40, right, you can use Pythagorean theorem. You could write out 30 squared plus 40 squared equals h squared. But you should recognize it's a 3, 4, 5 right triangle multiplied by 10. So at that moment, it'd be 50. But if not, go ahead. All right, so I'm going to put in 50 for h, and then we'll be able to solve dHdt. So here we have negative 200 plus 90, so that's negative 110. And then I would divide that by 50 to get my dHdt by itself. And the units in this problem would be units of length are inches, and units of time would be seconds. And I can reduce this to negative 11 fifths. Yeah, I'll write that. So the rate at which the hypotenuse is changing, dHdt, equals negative 11 fifths inches per second. Okay, so that was 9. Okay, looking on to 10. Oh, the ladder problem. Okay, so you have a ladder. The ladder's here, leaning against a wall. So the ladder's leaning against the wall, but the bottom of the ladder is being pulled out away from the wall at a rate of 2 feet per second. So if you picture the base of this ladder is being pulled out, this length here, which I'm going to call x, is changing, so it gets a variable. The other length that's changing is the length, it's the distance from the top of the ladder to the ground. That's changing. You know, as it slides down, that's going to be getting smaller. The length of the ladder doesn't change, so it's okay if I put the number right on there. You can only put numbers on before you take the derivative if they never change. Okay, let's see. It says the bottom of the ladder is pulled out directly away from the wall at 2 feet per second. So that is dx dt. And because x is increasing, I'm going to keep it positive 2 feet per second. For part A, they're asking us how fast is the top of the ladder moving down the wall. So at what rate is this distance y changing? So what is dy dt? And that's it. At no particular moment. Let me just check that. I can't see. Oh, when the foot of the ladder is 6 feet from the wall. So when x, so we're looking for dy dt when x equals 6. So we have dx dt, we want dy dt when x is 6. So again, length of the side of a right triangle, Pythagorean theorem. So we start out with x squared plus y squared equals 10 squared. We differentiate. So 2x dx dt plus 2y dy dt equals 0. The derivative of 100 is 0, any constant 0. Divide both sides by 2 to get rid of the 2's. Fill in 6 for x. Dx dt we're given was positive 2. Now, again, they didn't give us the psi, but that's okay because at the moment when x is 6, still a right triangle, right? So you could, if you didn't know it, you could say 6 squared plus y squared equals 10 squared. But you might realize this is just a 6, 8, 10. So if you solve for y, you would get 8. So I'm going to fill in for y, 8. dy dt is what we're looking for. So I'll subtract 12 from both sides. So I have 8 dy dt equals negative 12. Divide by 8. And so let me just move over here. Dy dt, negative 12 over 8, I can reduce that to negative 3 halves. Negative 3 halves, and the units of y would be feet, and time is seconds, so feet per second. So that's the answer to part A. So from part A, we find out that dy dt equals negative 3 halves feet per second. So now we know both dx dt and dy dt. I am going to erase the work that it took me to get dy dt. But I'm going to keep all this given stuff, information. Okay. Now they're saying, okay, so this ladder is sliding down there. At what rate is the angle between the ladder and the ground? So that would be this angle in here, which I'm going to name theta. At what rate is that angle changing at the moment, at that moment? So what we're looking for in part B is d theta dt. Now, if you got a right triangle and it involves an angle, now we're talking about trig functions. It's up to you whether you want to use, you technically could use any of them. The one I would stay away from here is tan, because if you write tan theta equals y over x, you're going to have to use the quotient rule. I mean, you have everything you need, but if you use either sine or cosine, you won't have to. So I'm just going to pick one. Let's say I use sine. So we know that this sine of theta equals y over 10. So when I take the derivative of both sides, I get cosine of theta, d theta dt, equals, remember, y over 10, don't use quotient rule on that. That's just 1/10 y. So the derivative is 1/10 dy dt. Now, we know dy dt. Remember, we just figured that out. That's negative 3 halves. So we're filling in the negative 3/2 here. We're going to solve for d theta dt, so leave that alone. But we do have to fill in cosine theta at the moment when x is 6, and if you remember, we figured out y was 8. At the moment when x is 6, cosine of theta would be adjacent over hypotenuse, so 6 over 10. So that's what I'm going to fill in here. Now, to get d theta dt, we can multiply each side by 10 over 6. If I multiply each side by 10 over 6, that'll knock out, that'll have d theta dt by itself. It will also knock out the 10 down here, and we'll be left with negative 3 over 12, or negative 1/4. So d theta dt equals negative 1/4. Theta is always measured in radians. And time in this problem was measured in seconds. So that's our answer for part B. All right. Number 11. A student is using a straw to drink from a conical paper cup. So it's like this. So inside the cup, you've got some liquid. Now, the whole cup itself has a height of 8. That doesn't change. The dimensions of the cup are not going to change, so I can put numbers on them. And the diameter of the whole opening is 4. I always work with the radius, so that would mean that the radius is 2. So we know the radius and the height of the entire cup. Now, inside of the cup, we have liquid, right? I kind of drew the surface here. Now, as he's drinking the liquid, the radius and the height of the liquid is changing. So for the radius of the liquid, I'm going to put on an r. I got to give it a variable. And the height of the liquid is also changing, so I'll call that h. Okay. The student is using a straw to drink from a conical paper cup whose axis is vertical, it's not tilted over, at the rate of 3 cubic centimeters a second. That means cubic centimeters, that's dV dt, right? And because he's drinking, the volume is decreasing, dV dt should be negative 3 centimeters cubed per second. All right. How fast is the level of the liquid falling? So what is dH dt? When the depth of the liquid is 5 centimeters. So when h equals 5 centimeters. So we have dV dt, we want dH dt. So first thing I'm going to do is I'm going to write the formula for the volume of a cone, because the liquid is in the shape of a cone. And I'll give you these formulas. The volume of a cone is 1/3 pi r squared h, right? The radius of this liquid is r, and the height is h. Now, you don't want to take the derivative now, because we don't know. If we want to get dH dt and we only have dV dt, we'd be missing dr dt. We want that r in there. But that's why with cones, you can use similar triangles. Using similar triangles will allow you to write a second equation to get rid of that r. So the similar triangles, so you can see it here, are this big one, right, and then this smaller one. They're similar. So if you set up a proportion, it doesn't matter how you do it. There are different ways to do it. But let's say in the big one, I have 2 over 8. And that would, in the little one, that would be r over h. Right? So radius to height in the big triangle would have to equal radius to height in the smaller triangle. When you cross multiply, you get 8r equals 2h. So the radius, the one we want to get rid of, that's what we want to solve for. The radius is 2/8 h, or 1/4 of the height. And you might have seen that when you looked at it. If you see that the radius of the whole container is 1/4 the height of the whole container cone, then you know the radius of the liquid will always be 1/4 the height. So that's what I put in for the radius before I take the derivative, because I don't want any dr dt's. So I put in 1/4 h here. We got to square that. Now if we square 1/4 h, we get 1/16 h squared. And if we move all the constants forward, 1/3 times 1/16 is 1/48, and we have the pi h cubed. So now we have a formula for the volume in terms of the h, the height. So now we can take the derivative of both sides with respect to t. 3 times 1/48 is 3 over 48 is just the same as 1/16 pi h squared dh dt. All right, so what do we know? We know dv dt is -3. So after you take the derivative, that's when you can plug in any known derivatives, any temporary lengths. So -3 equals 1/16 pi. H is 5 at that moment. Now we can solve for dh dt. So if we let me just rewrite. So this is -3 equals 25 pi over 16 times dh dt. So what I'll do is I'll multiply each side by the reciprocal, 16 over 25 pi. And I'll multiply each side by 16 over 25 pi. Doing the same thing, because that'll get rid of all that. Give me dh dt. So I would have -48 over 25 pi for dh dt. And putting some units in there, h is a height, it's a length in this case, h is a length, it's measured in feet. Time is measured in seconds. So that's the rate at which, I forgot the question. Oh, it says how fast is the level of the liquid falling. Like you could give me that, but technically the word falling already is giving you the fact it's negative, so you could just say 48 over 25 pi feet per second. It's falling at that rate. So the rate of change is -48 over 25 pi feet per second, but the rate at which it's falling, you don't have to give the negative because falling already indicates that. All right. Now, last one. We're doing this. It's going to be another one with the similar triangles. Remember, we see similar triangles like with the shadow problem and with cone problems, some cone problems, when we need to get it in terms of one variable. That's when we use similar triangles with cones. All right, so in this next problem, you've got a 30-foot lamppost. I'll just put that here. That's my lamppost. That's a big light bulb. All right, that's 30 feet. Then you have some 5-foot kid. That's him. And which way is he going? Boy, is that running at night, running toward a street light. So I'll make him running this way. Whee! All right, he's running toward the street light. All right. Running to a street light at 6 feet per second. So we got to get some variables on here so we know what derivatives we're given. So let's say, when the light shines, this is a shadow problem, his shadow is this length over here. Here's his shadow. So we're going to call that S. And we'll call the distance between the kid and the lamppost X. Okay, so let's first figure out what derivative they gave us using our labeling. That's why you got to label things first so you know what to call them. The young boy is out at night running toward a street lamp at 6 feet per second. So it's this length X that's changing. Now it's going to be decreasing as he runs toward it. So that's your dx dt is -6 feet per second. They want to know when he is 4 feet from the base of the lamp. So when x equals 4, A, how fast is his shadow length changing? So for A, they're asking us for the rate at which his shadow length is changing, ds dt. Okay. So we got to come up with an equation with an s in it. We've got an x. So what we're going to use here are similar triangles. We have a big triangle and a smaller triangle. They're similar. So we set up a proportion. So in the, I'll set up a proportion. You know, again, there are different ways to do it, but you could take corresponding sides. So big is to little, so I could write 30 is to 5, right? They're corresponding. And then you take another big side. Well, this whole side down here would be x plus s, and this corresponding side in the smaller triangle would just be s. Corresponding sides of similar triangles are in proportion. Now we cross multiply, so we have 30s equals 5x plus 5s. I'd subtract 5s from both sides, so we have 25s equals 5x. I'm trying to keep my s's and 5s looking different. I can divide each side by 5, so I have 5 times s equals x. There's our equation. So now we can take the derivative of both sides with respect to t. So we have 5 ds dt, that's what we're looking for, equals dx dt. Dx dt, if you recall, it gave us was -6. So we put in -6 here. So ds dt equals -6/5. Now s is a length, which is measured in feet. And dt, so time is measured in seconds. So for part A, the rate at which his shadow length is changed is -6/5 feet per second. Now, for the second part of this, it says how fast is the tip of his shadow moving? So the tip of his shadow is here, right? So in order to figure out how fast that's moving, we'd have to figure out at what rate this whole distance is changing. Let me call that C. Call whatever you want. So to figure out what rate the tip of his shadow is changing, I got to figure out what rate that length's changing, so I got to find for part B what dz dt is. Well, remember, at this point, we know what dx dt is, and we know what ds dt is. So the easiest way to go about doing this is to write an equation. Oops. Z equals x plus s. So dz dt equals dx dt plus ds dt. Now, if you remember, we just figured out ds dt was -6/5. And dx dt was -6. So -6, so that's -30/5 minus 6/5 would be -36/5. And that, again, you know, z is a length. It's measured in feet in this problem. Would be feet per second. And that is it. Woo! This was a long one. Okay, hope you enjoyed that. Bye.